Hello everyone. This is Shao Yecheng from Zhejiang University. It is my great honor to be here, especially to be in the same session with RI Lab. We use RI SIM. It is really a great engine. And this is the first paper from our lab. Our paper is about gait transition. Gait is an important part in quadruped locomotion. Animals can choose the most suitable gait and make transitions according to the speed, terrain, and its size, but it remains a challenge for quadruped robots to transit among various gaits freely. In this work, we train the control policy to learn multiple gaits and transitions under the guidance of phases. We use an LSTM neural network as the control policy. It uses the velocity command, the phase signal and the sensory data for input and returns the desired position for each joint. The neural network is trained by imitation learning. During training, we use for independent phases to generate reference motion. Each phase represents the position of the corresponding leg. The upper part stands for stance and the lower part stands for swing. Eventually, the combination of four phases can fully describe any possible gaits. Phases can be generated in two ways, that is, center pattern generator and manually designed functions. Improved Hopf oscillator is used as CPG in this paper to generate phases for common gaits like walk, trot, pace, bounding and transitions among those gaits. Manually designed functions are more flexible and can generate complex rhythmic gaits. The trained policy can be successfully transferred from simulation to real world. Guided by CPG signals, the robot can transit freely among all common gaits. Phases for each leg are illustrated on the upper right side of the screen, and the movement of each foot can follow the guidance of those phases even during transitions. When the phase of one leg is fixed, the robot can still perform three-legged locomotion, as guided by the CPG signals. With manually designed phase, the robot can dance to music in any designed dance steps. In this work, we train the neural network controller to learn the connection between phase and the corresponding leg. With the help of phases, we have extended the capability of a single controller to multiple gaits and free transitions. In addition, to further investigate the source of this ability, we measure the sensitivity of the trained policy with partial derivatives. In this heat map, lighter color means larger connection. We can find an one-to-one correspondence between the phase input channel and the corresponding leg. This map demonstrates that the policy can control the movement of each leg independently according to the guidance of the phase signal. Perhaps under our learning framework, the problem of multitask learning has been simplified to a single task. That's all for my presentation. Thanks for your attention.